With Professor Paz, we left off at chapter 12.
Chapter 12. And chapter 12, so let's go back through. What were some of the end chapters there? Let's go to 10. What was 10? Okay, let's not do it that way. Let's do it a better way. What were some of the last major topics of the last couple weeks in Chem 101?
The bonds.
What colligative properties?
The bonding.
Right, so colligative properties were some. What else?
Bonding schemes.
Bonding schemes, you mean like intermolecular forces kind of
Right.
stuff, right? Okay, so intermolecular forces. Those two gases were towards the end, or were that? No, that was early on, right? That's towards the end in 65, and 101 that was in the middle. Hybridization. So what were those? Those were, when we say hybridization, what was that? Overlapping atomic orbitals. So you're looking at the molecular orbitals, right? So these are some of the things we learned. Now, the interesting part of this, now,
Chapter
did
12
we do
was-
acid-base stuff?
Yes.
We did, right?
Yeah.
And
Solution.
what was the key in an acid-base reaction that was different than, say, any of the other types? So by an acid-base, what is that called? Neutralization out of a double replacement,
Right.
right? And then there were other types of reactions like combustion, right? Single replacement. What else did we do? Decomposition and synthesis or formation, right? Combinations, in other words. Okay. So what we're looking at in chemical kinetics are these, but let's make sure everybody's on board, because this, even though I said I wasn't going to review, just kind of make sure we do this. Let's look at something like this. Let's do a basic NaOH plus HCl gives me H2O plus NaCl. This is the liquid, all the rest is aqueous, blah, blah, blah. If I asked you, what are the reactants, what would you tell me? NaOH and HCl. Okay. If I put aqueous here, what does that mean to you? It's in water, and more specifically, is this together or separate?
Separate.
Separate.
Ionized.
They're ions, okay? Just to recall a couple things, make sure that we're all on the same page early on. Now, if I asked what this whole thing was, what would you say? Chemical equation. Okay, I'm distinguishing between a chemical formula and a chemical equation. Why am I doing that? Because I don't know how many of you, when I asked that on an exam, I said, what is the, blah, 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 for a formula? I got the whole thing. Right? I want to make sure very early on, this is a chemical equation, and these are formulas within that equation. These are the reactants, these are the products, okay? As we move into chemical kinetics. And kinetics indicate the direction and the speed of the direction that the reaction's going. Okay, so now we're going to break down this a little bit more from what we learned in 101. Because what we learned in 101 was, okay, let's just put these together. Did we go in 101? I think we did. Did we talk about strong and weak acids and bases?
Yes.
Okay. So then you know that if we have weak acids and bases and things of that nature, what happens to this arrow?
Goes back and forth. Equilibrium.
Equilibrium. And we're going to talk a lot about equilibrium. And I think I told you at that time, 5% is ionized, so you have 5% of this and 95% of that stuff. We're going to, in a lot of the stuff we're going to do, we're going to figure out what those actual numbers are for each thing. Okay, so we're going to do some fun stuff that's going to be a little quantitative, but hopefully I'll make it easy so it's not for those of you that don't like numbers. If I'm looking at this going to here, and I think I actually did talk about some of this in 101, so hopefully you'll remember some of this. And I want to assess at some given time how this is progressing. What would I look at? Can I look, so this is all I have.
Right.
So clearly I care about these things within it.
Right.
Can I look at
Concentration.
the loss in terms of concentration of this or this?
Yes.
Right? And or can I look at the gain of these?
Right. The rate of change.
So that's how we're going to figure out what the kinetics are. Okay, what the pace of something moving. If I start off with a whole bunch of this, and I wait 20 minutes and half of the reaction's gone, so I only have half of this, at this point, is the speed going to be as fast as it was here?
It's
Probably
gonna be-
not, right? Because I have more there, so
Correct.
more are going to interact more regularly, and then they're going to move forward.
Starts slowing
So
down.
the speed or the kinetics is going to change as I further progress through here until I get all of this.
Correct.
Right? It's going to change in terms of it's likely going to slow down. What things can I do to speed that process up from a biological perspective.
Catalyst.
Catalyst, absolutely. I take a catalyst, right? What does that do? It brings things together and it moves it faster. Catalyst, is that, when I say catalyst, is that something that's used in the reaction itself? Is that part of the reaction?
It's not.
No. In other words, you start here, it brings in reactants, and it kicks out products. But it itself, at the end, doesn't change, for the most part. In reality, of course, some of them are going to change a little bit or whatever, but for the most part, not enough to worry about it at this level. Okay. So that's a general idea of kinetics. So we're going to look at things, we'll talk a little bit about what kinetics are, we'll look at reaction rates, we'll look at rate determination, probably stop somewhere around rate law, reaction order. We'll get into integrated rate laws. It's a little more complicated here. Half-lives, graphing some of this and how the graphing relates to these things so that you could determine what these are based off of the graph. And then we'll get into things and other things that affect this process is clearly temperature would affect this process, right? Usually if I increase the temperature, I'm going to speed this process up. Collision theory, how often they connect or hit each other. And of course, the more times they hit each other, the more often that's going to happen, this process. Transition state theory, so when something goes from here to here, does it really just go from here to here to here to here, or is there some connection and transition that allows it to go here? Okay. Arrhenius' equation, which will weed out some other factors, reaction mechanisms. We'll break this up into how not just the general big equation occurs, but how the mechanism of each thing, how this connects, and then how they release. What's released is something else here connecting them, causing it to happen. So sometimes there's a lot more than what you see that goes on here. This is just the net part of what happened in this particular equation. Then we'll get rate laws and mechanisms. There's the catalysis for catalyst and enzyme catalytic.
We're not looking at like oxidation, redox?
We'll get to some redox later on.
Okay.
So when we look at, what was the outline? What was the syllabus? In the syllabus, we have some stuff coming up for that. It'll be a little later on, I think towards the end.
Oh, that's the lab exam? No, that's lab. Lecture, yeah.
There you go. Electrochemistry, electron transfer.
34?
Yeah. Okay, so if we start each chapter, so let me preface this too. This is going to be a little different than 101. Usually so we had 101 chapters that were some were long, some were short, we condensed them. The 102s, you have less chapters, but they're all pretty long. So there's probably a lot of slides on here. And that's why you see so much outline. So in 101s, as I usually do, I'll put the chapter, the heading, and then I'll put the outline. In 102, you'll get the outline, but the outline's much bigger. So I'm kind of bringing up a couple things just to keep you in context, but you're not going to see this for a couple weeks, most likely. This chapter, however many weeks I have it set up, what, 2 weeks or something? So they last a while because there are a lot of slides. Okay, so there's a lot of information in them. Go ahead.
Do we get access to the PowerPoint online?
No, you get access to the, it's a PDF file, but it's essentially yes. The difference between, so the question was, for those that didn't hear or haven't had me, is the PowerPoint's different than the PDF file you have. There will be some things added, especially when we do examples. So your examples won't be filled in, mine will be, presumably. And if not, we'll be filling them in, that's why they're left out. Okay. Basics of kinetics, the study of rates of chemical reactions. Okay. How fast does the reaction proceed to form products? How fast does it go from here to here? The speed, as I mentioned earlier. That's what we're looking at here. Okay. Hey, what's up, Nathan? How's it going? Can I make an announcement? Yeah, just let me know. No worries. So, okay, I'm going to stop right here since we haven't got too deep. And this is Nathan. So he sat through this class last semester. So, and then he sat through my 101, my 65, anything else before that. and he was the top student all the way through, and now he's in the tutoring center tutoring. He knows exactly what I want you guys to know even before I know it. Yeah. So you might want to listen to him.
Yes, I already know a lot of you guys. I've been seeing you guys, a lot of familiar faces. I'd encourage you guys to come to tutoring as soon as possible. Yeah, he introduced me. My name's Nathan. I'm on part of the team for the Science Success Center. I hope to see a lot of you guys really early because the more often I see you guys, I can tailor my tutoring for you a lot better rather than later where you come during finals week and it's hard for me to help you and identify what your strengths and weaknesses are. So I encourage you guys to come in as soon as possible, especially because 102 builds on itself as opposed to 101, which is a new topic every week. So yeah, I really hope you guys come by. We're in room 101. We're going to be open from Monday to Thursday from 11 to 7. And then on Fridays, we're going to be over at the library from 10 to 4. Hope to see you guys. Yeah, anyway.
Is there a website for them to go to yet? Or?
I think they're in the product. They're developing it. I think it's there. Yeah.
Yeah, it's up.
Yeah.
It's up already.
It's up already? Oh, okay.
It's up already.
Go
Yeah.
ahead and put your email just for contact.
Yeah. I also have a question. Yeah. Yeah. So Monday through Thursday, it's going to be open from 11 to 7. And typically, so because chemistry is the most demanding subject that we offer here, we're going to have a tutor there pretty much at all times to help you guys for 102. I happen to have an email that goes directly to me and other chem tutors for chemistry questions. I'm going to post it on the board so you guys can email directly. So, yeah.
And who are some of the other? Who are some of the other tutors?
So currently we have a soon-to-be grad student in chemistry. His name's Leo. We have Joaquin, who also completed the 102 sequence as well, the whole gen chemistry. We have actually have a grad student who got a master's in chemistry as well from Europe as well. So we have plenty of people to help you guys out, different types of people. We're gonna probably expand our room size as well soon. So that means that it won't be as cramped. But yeah, anyway, I'll put the email up. So.
Maybe I can even convince Nathan to come in here and give a guest lecture.
I missed that.
Now the class is complete.
He'd be really good, he just doesn't know yet.
Thanks, guys. Yeah, I hope to see you guys. Yeah.
Thank you.
Okay, so getting back to kinetics. So how fast do the reactions proceed? In other words, what time? So does this take 2 minutes? Does it take 10 hours? What are the reasons for the time differences? Is there some way I could speed it up? Is there some way I could figure that out? And that's what kinetics is going to discuss. Why is one reaction faster than another? And what are the dynamics of it?
Mm-hmm.
So we'll look at, so as I mentioned before, now I think was it in 101, I think we talked about Hess's law. Anybody remember
Yes.
Hess's law, right? And you remember how you would see the final equation, and in between you would have these intermediate reactants that didn't factor into the total equation, right? So there were extra things involved in this going to here, which caused more time because that's a whole nother reaction happening. So we'll look at the mechanisms to how that is, and that's based on different steps involved. So it's not always as simple as just this mixed with this forms that, right? There are things that could occur along the way that come in, that bind to this, that separate it, that cause this now to do something, and then it moves forward. It could just be that these two things come together, and then there's an intermediate where they bind temporarily before they form this. So it's like a partial or a transition. And we'll look at how each one of those things are the steps involved in those, which overall is called the mechanism. Okay, and that's some of the things we'll look at as well. So what kinds of things affect kinetics? So I think we talked a little bit about it. The concentration, right? The higher the concentration,
Okay.
the more of this is gonna speed it up,
Right.
It's gonna happen faster. So the rate is proportional to the reactant concentration. Is it related to the product concentration?
No.
Yeah.
React.
Well,
No, just the
no.
product reaction.
Well, actually, both of them, because if you have.
Could you think of ways that it would be? What if I start with 0 of this, because that's what this implies. So I have
Right.
0 of this, and I just start with this, 2 separate containers, then I mix them.
It's gonna start
Okay?
fast,
Now it's going to start fast. As this develops,
right? It increases and slows.
you're going to
down.
get less of this. So on its own, less of this, the reaction
Slows
the
down.
concentrations, the reactants are lower. That's going to reduce the speed. But you're going to have more of this, which also could interfere with them.
Right.
So it's not like they're sitting in there alone. So those things have to be factored into that. May not have a huge impact, but it could have some impact depending on what you started with. So if you start with a lot in a small area, and then you have some of this go, and then you have all this stuff interfering with more connecting, then that's going to slow it way down. So it can play a role, but the biggest thing that we're going to look at are the rates relative to the reactant concentrations. The higher the concentration, the faster the rate, presumably. Okay. The presence of a catalyst, that clearly is going to speed things up, right? It's going to bring things together. It's going to organize them. What does it do? So, and I think I showed you in my 101s at this. If I have things floating around, okay, are they automatically going to react? No. They could bump into each other this way. The more times they bump into each other, the better chance they have of finding the right fit, proper orientation. So what can a catalyst do? It could take two things, not only bring them closer together, but properly orientate them so the reaction can occur and then spit it out. So that speeds up the reaction. So that's what a catalyst may do. And it may be a biological catalyst, or it could just be something else, something that just attaches to it and brings things together. Okay. So the other thing about a catalyst is, and once again, with a grain of salt, it increases the reaction rate without being consumed for the most part. Every once in a while, there are different situations where some of it is consumed, and then you would have to account for that in any given interaction. And why does that matter? If you're ever doing research on something and you're trying to figure something out, and you just say, oh, well, I'm going to use this catalyst and it's not going to have any effect, it may. So you have to know those things. It may have a small effect that changes what you expect in your results, and therefore what you interpret your results as and what you publish potentially in the long term. And then all of a sudden you got to go back and retract it because well, my Chem 102 professor told me that they just are all consumed or not consumed at all, and now all of a sudden I realize some of it was consumed. So you got to, most of the time, 99% of the time, that's going to be true or very minor, but every once in a while you could have something that is consumed even though it's a catalyst. Temperature, as you increase the temperature, you would have expected the rate goes up, so they're proportional. This little alpha signal just means proportional. Rate goes up, temperature goes up. And lastly, the surface area. Okay, so if I'm looking at a reaction that's at the top of the surface, so everything underneath is not part of the reaction, then the greater that surface has with whatever it's going to interact with, that's going to speed it up, right? So the larger the surface area, usually the better, the faster the rate, let's say. Okay, so the rate is proportional to the surface area of the reactants. All that makes sense? So far, no problem? Can be an easy class, easy semester, right?
Let's go.
That's good. Absolutely. Hopefully. Okay, so let's look at the reaction rates, how it's defined. So you increase the molar concentrations. Okay, let me sidetrack a little bit. How am I doing on time? Good. Okay. What is a concentration? Maybe I should make sure that we're aware of that. Most of you probably know, but let's make sure. What is a concentration? What's the definition of a concentration? The amount of solute divided by the amount of the solution. And the solvent and the solute make up the solution. There are concentrations that are not used very often, but you can find them, like normality, which is the amount of the solvent that you're dividing the amount of the solute by. What do I mean by amount?
For morality?
For anything, just what does amount mean? How can I define that? What am I referencing when I say some basic questions? Sometimes moles would be an amount, mass would be an amount.
Yeah,
okay. What are the units associated with moles? Moles. That's a unit and a type of thing, right? What about mass?
Kilograms.
Grams, kilograms. See, there you have a different unit, but that's what's referencing the mass, just to keep these things in mind. So when I say molar concentration, I'm talking about molarity, which is the common concentration used, and molarity is something with solute, moles of solute per liters of solution. So there I'm talking about the volume of the solution.
Right.
Okay, so remember, you could also have it in terms of volume. Okay, so that's what I mean about amounts. Okay, so when I say this, the molar concentration, I'm referring to the moles of this, which would be something, say, 1 molar and 1 molar. And so if I increase that to 2 molar, does that speed this up? Or does, if I increase this one to 2 molar, or do I need to increase both? And how do those things have an effect? So what I'm looking at here is the increase in molar concentration of a product per unit time. In that case, I'm looking at the product here. So I could define the rate as this goes up, or as this does what? Goes down. Absolutely, because this is the direction of the reaction.
All right.
Okay, so I could look at it either way. And how do I represent that? Delta, which is change, of the constant. So these brackets mean concentration. primarily you're going to see that in terms of molarity. Where did you know that from? Acid-base reactions, if you recall. And the change of time. Okay. So let's say the concentration from time 0 to time 10 seconds. So that's 10 minus 0 is 10. My change in time is 10 seconds. And how much product? I started with 0, and it went up to, say, 3 molar. That's 3 divided by 10. That's my reaction rate. Okay. That makes sense? Let me make sure this is clear. Delta means change. What does it mean if I put it over the arrow here? Heat?
Heat applied, yeah.
Everybody said heat. I heard that. I know. It just came out differently. Right. If I put it over here, that just means heat. If I put it outside of that and in front of something, then that just means, just say this is product, then this is the product final minus the product initial. So whatever this is in front of, it's the change in it, and you always go final minus the initial of whatever it is. We saw that, I think, when we looked at energy, right? Q equals M times S times delta T. Delta T we saw that with, right? So temperature final minus temperature always means the same thing. So that's what this is saying. Temperature final, or time final minus time initial, product concentration final minus product concentration initial.
The delta Q, is that always molarity, or in terms of molarity?
Usually. If it's different, it will be stated.
And the time's always in seconds, I'm assuming?
Usually, it could be minutes.
Minutes, like milliseconds?
I also could ask,
Give it to you in minutes and
well, I
seconds.
could give you, so you'd get a chart to figure that out, right? And I'd say between, say, 10 seconds and 30 seconds, and so then you'll make what the different product concentrations are at that point. And it could say seconds, but then I could ask for the molar concentration per unit time, and I could say I want to know the moles per minute.
Okay.
So then once you did it in the seconds, you would then just convert using a conversion factor, right? 60 seconds per minute with the 60 on top, and 1 minute on the bottom, and then cancel. It could be given in a different way. Absolutely. Okay. And there's a plus sign. Is that relevant?
Yes.
Yeah, how come?
That'll be the product.
Because you're making it.
Right.
So it's going up.
Correct.
Right? You're going this direction, you're talking about products, so you're looking at the concentration of this one or this one, and you're looking at it going up.
Correct.
It's increasing over time. So that's why it's positive. Okay, so obviously we already know the other one. A decrease in the reactant concentration. In that case, here's R's for your reactants. This whole setup's the same, and the negative sign means that it's decreasing. This is, you're losing it, so it's becoming minus. So ultimately, I'm asking for what? The reaction rate. Here. Okay. Point of confusion? Pointing out something right here for you guys. The reaction rate, should that be positive or negative?
Negative.
Does it matter?
Negative.
I'm asking about just the rate.
Ne-
The rate
Oh, the
itself
rate.
should be what?
The rate, yeah, positive.
Positive.
Right.
So, why is the negative there?
To tell you
Shows
the reaction.
the direction.
Finus minus initial is going to give this here. Is this ever going to be negative?
Negative.
No, that's a change in time. Time only increased. Will this be negative? Yes.
So
Negative times a
Oh.
negative, positive. So they'll always be positive. That's why the negative's there. Okay. When I'm asking about the reaction rate. That makes sense? Anybody uncertain about that? If you are, mark it down. By the way, just because you don't, you're not sure of something, does not mean that as you're learning it immediately, and I'm the same way, so this applies across the board. It does not mean that you could quickly figure out what you don't understand and then articulate it in a question. So don't feel uncomfortable going home figuring it out. Just notate, though, for sure where you weren't quite clear on something. Notate what I say. Go back and look at it, and then if you have additional questions on it, now that you've had time to think about it and ask, that's usually where you're going to come up with the best questions. And then just ask either, privately or in class you can ask, because you're probably going to help other people who are struggling with the same thing when they first hear it. I could almost guarantee that if one of you have a question or uncertain of something, at least 3 or 4 others in this class are thinking the same thing. Okay. Just people get nervous and don't want to admit it. Somehow that makes you less competent, which is about as dumb as it gets when you think of that way. Okay? What I think is less competent is not knowing what you don't know and thinking that you know everything. Just to keep that in mind. One of the things you learn in grad school is that how little you know. is probably the best lesson that you could learn in grad school. Not that you come out of undergrad thinking you know a lot, right? So you get pumped up and I know so much, and then you come out of graduate school and you're like, okay, if you really learn something, you realized how little you know. And even more so, how to figure out things you don't know. Like how to recognize you don't understand something and then how to figure it out. Okay, so keep that in mind. There's no expectation for you to know anything. You don't look stupid by asking something that you don't know. There's no reason for you to know it. Okay?
So the reaction rate's always going to be positive?
That's right.
And the delta R is going to be negative and delta B is going to be positive?
Yes.
Okay.
Yes, yes. And that's because final minus initial, the final here is going to be less than the initial. So you're going to have a negative. So then the negative times a negative is a positive, so the reaction rate will always be positive. Okay. So I have this here, H2 plus I2 gives me 2HI. Looks like it's a balanced equation. Here's something I want to point out. This will play a role. I'm not going to emphasize it just now, but I kind of want to introduce it. The idea that you have gases in here as your types of physical states of these reactants, that's relevant. I'm not going to emphasize it just yet, but at some point in this class, you're going to realize that that's a really, really important component of a lot of things we're going to discuss this semester. Because as a result of that, I could actually figure out quite a few things if the gas is changed from one thing to another. So if I have 2 moles of gas on one side, 3 moles of the other, what's going to happen to the volume? It's going to expand.
That's right.
So I could start assessing things based on the idea of gas and gas molecules. Also, if something's going to interact with something, what do they usually need to interact with the exception of an aqueous type of reaction? Gas, right? Remember, so when we did Hess's law and we looked at sodium chloride development, right? They both at some point had to be gases, right? Because that's what's exposing the electron transfer. Okay, so gases do, this is a pretty relevant thing. We'll talk more about it later. I just want to point that out. I see it. So the rate of disappearance of H2, what would it be?
Rate of 1/2?
Be the rate of the change in H2 over the change in the time.
Right.
Okay. There we go. Not too hard.
And for this one, because it's on the reactant side, you put a negative sign, so it would end up positive.
It would if you were solving it. But since we're not solving it, I'm just saying, what is the rate
Yeah,
of the
yeah,
disappearance?
okay.
Yes, absolutely. But if I give you numbers, yes.
Right.
That's it. That's
What does it mean exactly by saying disappearance?
that the concentration of the H2 as a reactant over some time is less.
Okay.
And what is that rate? So how much less per that time?
Decrease it.
Okay, so the decrease in the molar concentration of H2. What would it be for the I2?
Same thing, 1.
I just substitute what?
H2.
H2 and I2, right? Okay.
Right.
What would it be for HI?
It'd be 1/2.
Ah, there's something there, huh? What do we do with it? There's a coefficient. What is that thing? That thing's always annoying, right? Because it throws off like all the basic concepts. It throws in, what would I call that? What am I looking at there? I'm dealing with stoichiometry
Right.
in the balanced chemical equation, right? So yes, that will play a role. We'll talk about it in a second. Okay, what's the time there? Okay, so the average rate over the time interval that you're looking at is what that is, right? Because as we saw earlier, if I have a lot of this and then I reduce this, then this rate is going to slow down with less concentration. So when I look at the time frame, I'm looking at where it starts higher and ends lower, the rate itself will change per time. So if I say 10 seconds and then I look at 1 second intervals, each 1 second interval should reduce the overall rate as I go down because I'm decreasing the amount of the reactant. So this is an average over that time frame. So I could always take, so at 10 seconds, I could break it up into 1 second intervals, 5 second intervals, half a second intervals, and each one of those will be slightly different. So this is the average over whatever that time frame is. Okay, let's look at a chart. Concentration and molarity, time. I have 2 curves here. This curve is representing the HI from that last equation. Maybe I should put that up, make sure that we're looking at the same equation here. 2, gas, I2, gas, and that's going to go to 2HI as a gas, okay? So, when I do this, you can see the product, you can see the reactants. At time 0, how much, this is the time here, this is concentration, how much concentration at time 0 should I have in this equation? For the product?
Oh, 0.
0. So that curve starts down. As time goes on, 20 seconds, 40 seconds, 60 seconds, you can see the curve goes up, up, up. No big deal, right? Now this one here, so they're only giving you the H2, they're not showing the I2 here. So the H2 starts, whatever this is their concentration, say it starts about 1 molar at time 0. As soon as I mix it with the H2, is that going to go down?
Right.
Yes. And you can see how they go down, by the way. So it starts a little steeper, goes up a little steeper at some point. This is the midpoint, right? This is where I have the same amount of HI as I do I2.
H2?
Or
They're the same.
H2, yeah, would be the same, but H2 as well, yeah. Only because it's a 1-to-1 stoichiometrically, yeah. And so at that point, then past that, I have more product than I have reactant. And I just relative to the time frame. So if I want to see the rate at any given point, the rate here is going to be higher than the rate here in loss, and it's going to be higher here in gain than it is up there. If I look and I say I want to go between, what is this, 30 and 70 seconds, 70 minus 30 is 40 seconds, right? So that's what would be the rate. And then I say, okay, where does that cross over to? Let's say that's 1.5 and 1. So 1.5, if I'm looking at up here, that's gaining. So 1.5 minus 1 is going to be 0.5. 0.5 divided by 40, that's my rate. And that would be the average rate over that time frame, which then would hit the curve right there. That's where the tangent line would go across. And that's the position that you're looking at in that context for the rate of the reaction, in this case, of the development of the product. And that's all this is. Go ahead.
What's the dotted line?
Yeah.
Which one?
The dotted line that's going through the dot on.
Oh, that's, you mean here?
No,
Yeah.
the-
Oh,
that's
the
the-
long
the-
one that goes
the
through
long-
both
the one that
triangles.
goes-
Yeah.
Yeah,
This
that
one?
one.
Yeah.
That's just showing the position that you're looking at for each one of the, either the reactant or the product. At that moment, this is the rate of loss of the reactant and the rate of the product gain.
Oh, gotcha.
It's hitting it at the same time frame.
So you can put it anywhere.
Yeah.
You can be
I
anywhere.
can try it here, then I have to, draw my whatever on both sides.
Got it.
Okay.
Okay.
Cool.
Okay. So concentration product increases with time and reactant decreases with time. Now, when I show this, I mean, this is early on, but as we go further and you see charts like this, just make sure you understand, if I gave you something like this and took away something, I could ask you something about the chart. And then you'd have to be able to explain the chart, right? That's what I'd expect from something like this on an exam. So I try to give you some insight into the types of things to think about as you're studying. It may not be this particular chart for instance. This is a little early on, and this is kind of a simple chart, but it could get more complicated. And in that context, I may pull, like I may get rid of this and say, which one is the reactant? That might be too easy, but I could say, if I have a point here, what is the change in time versus the change in loss of that reactant? And it may not be H2, it would be something else. So those are the kinds of questions that I may ask, or the types of questions I will ask throughout the semester, just to give you a sense of what I look for. Okay, so here's a chart, I guess, of that. And you have charts like this. So here's your time, and this is the time, and this is the concentration of H2. So you can see at time 0 you have 1 molar. Over time you have different molarities, right? And if you look at between 90 and 100, your drop is 0.03. And if you look at 30 and 40, your drop is 0.1. The rate is much faster here than it is here. Okay. And then this is the change of H2 over the time. So if I break that down each second, you can see that here. Oh, here we go. Okay. So this is what I was saying here. You have your 0.1, and down here it's 0.03. The rate decreases as you decrease the concentration of the reactant because you have less of it to react. And of course, you also have some product now that's interfering with it. And then these are the
Change.
time frames. And then if I put this over this, here's the rate of that reaction. Okay, and you see this is positive because this is negative. You put this in, this is loss. There's your negative there. Negative times the negative makes the whole column positive because you're just looking at the reaction.
So if you had way smaller subintervals, you'd have a lot more accurate rates, right?
Yeah, absolutely.
Is that sort of like what-
At that point, but now, and we learned this a little bit in 101, what's more relevant, to have a more pinpoint position on the rate or the overall rate of the reaction? Depends sometimes, right? What are you studying? Right? There's no, so you may want to say, hey, at this point, I want to put something into the reaction. So where is that point? Now you want a more specific point. You want to break it down to a second, half a second, whatever you can, right? Whatever your technology allows you to. But what if you just want to know, I want to mix this amount and this amount, and I just want to know what the end is? What's the overall rate? How long is that going to take me? Well, then it's more broad. So I like the question, though, because it does bring that thought process of what is it that you're trying to accomplish. And that matters. Okay.
Is it important to know the midpoint? You see where they actually come at the same
It
rate?
could be, maybe not, depends on what you're doing. Not by instinct would I say it's more important than any other point, unless that point means something to you and what you want to accomplish, right? What you want to accomplish, if you want to stop it at that particular point. So going back to Karash's point, let's say right where they cross over, let's go back. Right where they cross over here, and I wanted to have the exact amount of concentration of what is this, H2 and HI,
Right.
then for whatever reason, then maybe I could put in something to stop the reaction. We talked about catalysts. Maybe I want to put an inhibitor in at that moment to stop it, to try to get that for whatever reason, because I want to I only want so much HI, and I want it mixed with this amount of H2.
Buffers would do that?
Or maybe I could do something like add only half of the I2 and use this in excess or something like that, right? So you could think of different ways that we could manipulate it. So if I wanted that for some reason, because then I'm going to take this and maybe do another reaction where I add something else to it to get something different, then I would care about this. It all depends on what I want to do. I'm just giving you some examples off the top of my head of reasons why I may want to stop it there or not, or anywhere else for that matter.
All right.
Reaction rates, reaction proceeds, okay. Any substitutes be used, express, okay.
What was the buffer doing for us?
Buffer.
Yeah. Did we use, we didn't actually go deep into buffering, right? It was only 6
So
months.
the question here are buffers. Buffers matter depending. The idea of a buffer is to create an environment that your reaction will happen optimally.
Right.
Okay, so for example, if I'm in a biological system and I want my polymerase to transcribe something, I'm probably going to need a certain amount of zinc, a certain amount of potassium and sodium and whatever else. So you'll figure out what that optimal buffer is, and then you'll do the reaction where you add your reactants together in that buffer environment, because that will produce the most for you. You'll do a lot of control experiments to figure out what that optimal buffer is. I haven't talked about buffers yet, but since you brought it up, that's the context that you would use it in and care about it for.
Thank you.
So reaction rates, okay, so concentration reactant decreases, nothing new there. So any substance in this reaction can be used to express the reactant rate. That should be pretty obvious. We can look at this decrease, or this increase, and that too does play a role stoichiometrically. Okay. So the rate of disappearance of H2, we already know this, so we're saying the same thing over again. Okay, these slides need to be adjusted. Here's the I2, same thing. And the rate of formation, in just the rate of formation, I'm not including this stoichiometrically yet, but I will, is just the change of HI over delta T. Now, these are all positive, so I took out the negatives here because I'm not actually solving for anything. And I also, in this particular equation, I did not include the stoichiometric ratio because this is really just what I'm looking for when I specifically ask for the rate of formation, nothing else. Okay. Which means that with all the other things that you're going to learn stoichiometrically and knowing the negatives and positives, when you actually have the data, then you translate it so that you end up with this is what you're trying to solve for. So let's see what I mean by that. Oh, okay. So this is, okay, so I guess this is the really slow version of this class. So here we're going to emphasize that it's always positive, which I think we already know now, right? So I'll move through that. The rate of formation of a product is positive, that's obvious, and you get rid of the reactant, it's negative, and they both end up positive. We've already had this discussion. Okay. Now let's plug in the stoichiometrically, what this matters. So I find this a little odd in how it's described, so I'll give you a more, at least in my opinion, intellectually an easier way to think about it, but let's go over the slides because some of you may like it this way. The rate of increase of HI is equal to the rate of decrease of H2 times 2. Okay. And then if I go ahead and divide by 2 and divide by 2, the rate of increase of HI divided by 2 is equal to the rate of decrease of H2. H2, that divided by 2, gives me the HI. Because if I go back to here, let's go back to one more. Here, this is the rate of HI. But since it has a 2 there, then I have to divide by 2 to get this actual rate here. So I just like to think of it stoichiometrically, you just divide by that number. And that will equal these ones since they only have a 1 coefficient in it. So if this was a 3, what would I do with the delta H2? Divided by 3. Absolutely. The negatives stay negative if it's a reactant, and positive if it's a product. So I just look at the stoichiometric ratio, which, does that matter? Absolutely. So if I want to find just what one of these are, which is what the rate of formation is of just this, I'm just looking at the rate of, I'm not looking at the rate of formation of 2 of them. I could do that, then I just multiply by 2. But the rate of formation, it goes back to, okay, let's look at it this way, because I know this is problematic at some level. You're going to walk away and say, okay, I get it, and then you're going to do it on an exam, and I'm going to go, I know this. Do you remember on report forms in 101, for those at least that took it here, when it said, what is the product, or it said, what is the precipitate? Okay. So for those of you that got over giving me the whole chemical equation, right? Because it asked for the formula of the precipitate. So let's assume you were able to put the formula. How did you find that formula? You did the balanced chemical equation, and then you did some net ionic equation here, and you ended up with that 333.
Right.
And what is the formula of the precipitate? And then you would say barium sulfate. 3 barium sulfate. The formula isn't 3 of them. The formula is only 1 of them. Right? Why would you put the 3, right? When you think of it that way, you're like, yeah, well, because it said 3 in there. And by the way, in there, you were supposed to cancel that out and have the lowest ratio, if you recall, right? Because it would have been 3 barium, 2 plus, 3 sulfate, 2 minus, 3 BaSO4 solid. And then somehow the 3 stays there, you lose half a point, and then you give me 3. And I'm like, I'll just mark off the 3, but I really should be taking off to get that through you, to make sure that you do that. Same thing here. It's not asking for the rate of formation of 2. It's asking for the rate of formation of 1. But the equation tells me the rate of formation of 2. So I have to divide by 2 to get the rate of formation of 1. Intellectually, to me, that's much easier than trying to say 1 is equal to times 2 of the other, right? And of course, then this should equal that, of course, from this, right?
Yes.
When I set them up, but this should equal this divided by 2, because it's 2 up there. And that's all that other slide was saying, times 2. I like to think of it just through the stoichiometric relationship. Is an easier way, at least for me, to think about it, because I think that's odd. When you throw the 2 here, you're like, the reason it's odd is because it's like, no, there are 2 on this side, not that side. That's the instinct for some of us in how we think, right? Okay. Does that make sense? Everybody see that?
Yeah.
Okay, good. Okay, so what do I have here? Oh, we have examples. Cool. We're almost out of time. Let's see if we can get through an example. So we have this type of chemical reaction, so this looks like a generic reaction. And we want to write the rate expression of each of the reactants and products. So rate based on A, what would I write?
1 over 3,
Change of A over 3 change of T.
3 delta T.
Is it given in the notes?
No.
No, good, okay, cool. I sometimes do that, and then all of a sudden everybody starts saying the right thing. I'm like, hey, how did they know that? I wouldn't have known that if I was you. I just looked at it beforehand, that's how I know it. I've done this a long time.
1 delta A.
So we're looking at, is it a reactant, A? Or a product?
Reactant.
Reactant, positive or negative? Let's start.
Negative.
Negative. Stoichiometrically, does it have a coefficient in front of it?
Yes.
So it should be 1/3, negative 1/3.
Right.
The change of
Delta A.
A
Delta T.
over the change of
Delta T.
time. That's it. Right? Oh, good, I'm right.
Would we include the negative sign though, even though we don't have numbers to actually plug
Yes.
in?
At this point you do, because if you did have the numbers, this would then become positive. And because it's asking it based on this equation.
Okay.
So now what do we, oh, let's do B. All right, getting sophisticated. This would be harder than the last one. That's just negative concentration of change in concentration of B over concentration of time. That one's pretty straightforward. I'm sure it's going to ask about C, okay. 1/2 change in concentration of C over delta T.
Yep.
Okay, and D, 1/4. Okay. No problem, go
So
ahead.
the negatives only it's basically just saying there's a decrease in the reactants, and then the positive is just an increase in product.
Exactly. And then when you actually, if you had numbers to put in, this is positive because it goes up, so you're taking the final is higher than the initial, so this stays positive.
But
This one, the reactant, the final or the further one down in time is going to be less than the initial, so this will come out negative, so that's how they'll become positive overall. That's why the negative's there. So you could think about it as a loss, but then when you're just talking about the rate, you're not really thinking about the rate of losing or gaining. It's just the rate that it's doing something. Okay, so what do we have here? Okay, so we'll just put them all together. These all equal each other. So within this balanced chemical equation, those are the rates of each one within the equation relative to each other. Which is everything we just did, putting them all together. What's that? Okay, so that leads us to 2. Looks like we're right at the time frame, 12:25. I'm sure all of you want to stay and do more, but I'm going to let you go. So I'll see you. This is Tuesday, Thursday, so I guess the next time I get to see you is in a couple days on Thursday, and then we'll pick up from here, okay? Okay. Enjoy lab, and I'll see you in a couple days.
Professor,
Yep.
just a quick question on. Just jumped a little bit ahead. This the rate of actually will grab the rate of change of this and times the 1/3, right? That would be accurate? Okay. Cool.
So you didn't call my name.
Okay.
I enrolled in